Video 2 of Reflections. When we last left off in video 1, we had Justin Bieber crying. Right, Justin? Shut up, I'm not crying. You were crying too, Justin. Don't worry, you got the problem right. Anyway, we're going to talk about reflections now more graphically, where rules may or may not apply. Okay, so imagine we've got this butterfly here, and butterfly is very nice because he is symmetric between his body here, or his whatever this part of his body is called, the thoracic or something. I don't know. I failed biology. Um, but here's what I want you to start to notice. All over here, here are my pre-image, and here are my image coordinates. I tried matching up as closely as I could each pre-image to its image on the butterfly. Okay. Now, the red line is our line of reflection, what we've reflected across from our pre-image to our image. But there's some special properties going on between each pre-image, its image, and the line of reflection. Okay, so I'm going to draw these connections here between pre-image and image for all of these. Notice the distances aren't always the same, which is fine. But what do you think is going to be true about the distance between the pre-image and the line of reflection and the line of reflection to its image? Well, it's looking like those are even, right? They should be congruent, that this piece is congruent to that piece. Okay. Does that look like the same thing's happening with B and B prime with the line of reflection? Yeah, sure does. So what we might say, instead of these two pieces being congruent to each other, is what does the line of reflection do to the whole distance between a pre-image and its image if it's cutting it in half? Well, we had a specific term for that, aka bisected, bisecting, whatever tense verb you want to throw on there. So the line of reflection is bisecting each pre-image to its image. But there's also something else at play here. Notice the certain angular properties between the line of reflection and the distance, if you will, this segment between the pre-image and image. What kind of angular property does it look like is going on there? And if you said, I believe it's a 90-degree angle, Mr. G, you would be correct. So the line of reflection not only does one thing, it does another thing. Number one, it's going to bisect things, and it's going to be perpendicular to things. Fantastic. So let's talk about this now. A reflection is a transformation that creates a mirror image, obviously. So all the underlined stuff here, this is stuff that's in your notes that you'll need to write out. The original figure is reflected in a line called the line of reflection. The reflected image is congruent to the original figure. So in this picture here, they're showing that the original figure is this flag ABC, and that if we were to reflect it, if you were to look at it in the mirror, that really flag A prime, B prime, C prime is the same exact size, okay? Which hopefully makes sense, right? If you look at yourself in the mirror, then what you see and what your mirror would see of you would be the same exact size and image. The orientation, though, of the reflected image is reversed, meaning look at ABC, look at which order it's going in. It's going in a clockwise motion, but in your reflected image, it's going counterclockwise. It's like when you hold up your right hand in the mirror, it looks like your left hand is being held up by your mirror image. It's that same type of concept. And here's the most important part that we recently discovered. The line of reflection is the perpendicular bisector of the segments joining the corresponding points. We just mean the pre-image to its image coordinates there. Okay? So not only 90 degrees angles being formed, notice there's our 90, 90, 90, but we're also bisecting this distance between pre-image and image. So notice that that distance is congruent to that distance, this to this, and that with that. So we're going to do a few examples together. All right, so the first example here, we're going to take triangle PQR, there we go, and we're going to reflect it across the y-axis. Well, we had a rule for the y-axis, right? It was x comma y, And if it was the y-axis, then the y was what stayed the same, and the x was the thing that switched signs. Well, we could do that, right? We could figure out the coordinates for P, Q, and R, and then use the rule, and then take those image coordinates and graph them and connect the dots. But instead of doing that, let's learn something new with the graph. So you don't have to use the rule, because I think the rule is going to take you longer to use anyway. So here's how we're going to do this. Let's start with Q. Q is the closest to the y-axis. Now, how far away is Q from the y-axis? Well, it's 1 away. All right, so if we want to reflect it over on the other side, guess how far away from the line of reflection, the y-axis, I would need to go to find Q prime? Well, I would need to go the same distance away that Q was from the line of reflection. So Q prime just needs to go 1 away in the same direction. So there's Q prime. Let's go up to R. R is the second closest. It's 2 away. So I need to jump 2 over in the other direction. And there is R prime. P, how far away is P? Well, P, if I just kind of look up here real quick, it's at the x-coordinate of -10. So I don't have to count all this. I know that this is 10 away. So I need to jump 10 over in the other direction. I'm not going up or down anything. I'm just jumping directly left and right in all of these cases. So now if I connect my dots, R prime, Q prime, Q prime, P prime, P prime, R prime, does it look like P prime, Q prime, R prime is the reflected image along the y-axis of triangle PQR? And yeah, this distance and this distance are congruent. This distance and that distance are congruent. And this distance is congruent to that. And all we were doing was having these horizontal distances here, which are going to be perpendicular to the y-axis, which is vertical. So there's our 90-degree perpendicular property coming into play. So we're good. Oh, well. So we don't really need to draw in all that. That was just extra stuff. So there's an example of going across the y-axis. Now, we don't have a rule for y equals 3. At least we don't have a rule. I don't have a rule for y equals 3. Maybe you came up with some special way in the last video for doing crazy stuff. I don't know. So first we need to discuss, where is the line y equals 3? Well, y equals 3, here's the y-axis. There's the 3 on the y-axis. So do I do a straight up and down line or a horizontal line? Which way do I go here? A lot of people want to tell me, oh, you do a straight line up and down. So like that? Okay. So does that mean if I wanted to graph the line y equals -4, it'd be the same line? Well, that doesn't make much sense, does it? Two different lines really are the same line graphically? No. So you don't go vertically with a y equals line. It's going to end up being horizontally. So let me get a thicker line here. So at y equals 3, you want to cut across and make it perpendicular. And there's a line we want to reflect across. All right. Now, the one thing I notice is this line's going through my triangle. So things are getting interesting now. So if R is on the bottom side of the line of reflection, when I reflect it, it's going to be out above it. P is above. When I reflect, it's going to be below. Q is below. When I reflect, it's going to be up. So things are going to be switching around here, which is fine. So let's do it. Let's start with Q again. Q is the closest to our line of reflection. It's 1 away. It's 1 away vertically. So whenever I reflect across, it needs to go 1 above the line of reflection. So there's Q prime. Now P is 3 above the line of reflection, from 6 to 3 here. So I just need to drop 3 below. So P prime just happens to be, let me just move P out of the way there. P prime is going to be right at the origin, 0, 0. And now R is how far away from the line of reflection? Well, there's 3 spaces. And there's, let's see, R down here is at -4. So there's 4 more spaces. So there's 7 altogether. Or you could just count 1, 2, 3, 4, 5, 6, 7. So I need to go 7 above. So 7 above 3 would put me up here at 10. I just need to be in the same vertical line. So there. And there's R prime. So now let's connect the dots. P prime, Q prime, Q prime, R prime, R prime, P prime. So does it look like that triangle PQR is a reflection of P, or reflected would make P prime, Q prime, R prime? And yeah, it looks pretty good. I mean, this particular shape, if I'm just breaking the shape down into smaller subshapes, this is looking like it's symmetric right along here. This other crazy looking shape, oh, I didn't want that color. This little doodad thing, it's looking like it's being perfectly reflected over here. So yeah, I think we did a pretty good job. And you can think of, man, now I can make all these like cool random shapes. This kind of looks like a stealth bomber kind of from above. All right, the last one we're going to work out together. Now we're going to do not a normal, like we're going to reflect across a vertical or horizontal line. Now we're going to go across the line y equals x. So first we need to graph y equals x. And again, I mentioned before that y equals x just means if you don't know what it is, just start plugging numbers in for x and what are the y coordinate, and then graph that point. So if x was 0, well, that means y would have to be 0. So we're at the origin. If x is 1, y is 1. So we're at the point 1, 1. And so we start getting all these points, 2, 2, 3, 3, 4, 4. And if we start lining everything up, we're going to get our line y equals x. So there's the line we're going to reflect across. All right. Now, let's start with Q again, because it's probably the closest, or maybe R is, because these RQ and our line of reflection look like they are parallel to each other, but we'll see. Now, Q needs to make a 90-degree beat here for the line of reflection, and it needs to reflect over the same amount. So I think Q prime is going to be somewhere in this vicinity, but I can't count diagonally. I can only count vertically and horizontally. So how am I going to do this one? Well, here's what we're going to get to do. We kind of get to use kinda slope, but not really. It's going to have that feel to it though, okay? So work with me. Q, I've got some choices. I'm either going to go this way to the line of reflection horizontally, or I can go vertically down to the line of reflection. Which way can you go? It doesn't really matter. You pick. I'm going to go vertically. I always tend to go in a vertical motion here. So how far away is Q vertically from the line of reflection? Well, it's 1, 2, 3, 4, 5 till I get to right here. Now, I still need to move 5 spaces, but not vertically again. I need to move kind of the perpendicular way of vertical, right? Because we needed to do the perpendicular bisector, except our perpendicular thing is coming in at a different spot than where we would expect it to be. So we need to go now 5 horizontally across. So now 1, 2, 3, 4, 5. There's where Q prime is located. And if I wanted to look, just to make a quick double check here, from Q to Q prime, I can make that distance right there. This distance, does it look like it's the same distance as that much? I think it does. Does it look like it's making a 90-degree angle with our line of reflection? I think it's making a pretty strong case there. So we don't need that line. But that's how we're going to work across y equals x. And that's how you also similarly work across y equals negative x. All right, so let's go R. So again, I like going down and then across. So let's see, R is 1, 2, 3, 4. It's 5 down. So let's go 1, 2, 3, 4, 5 over. So here's where R prime is going to be located. Now, just keep in mind, we did have a rule for y equals x, right? We could just flip the position of x and y, and we didn't have to switch the sign. So you could still do that for this problem, but I'm just trying to save you some time here that hopefully this now makes quite a bit of sense. P, oh boy, P is a long ways away here. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And now I need to go 14 the other direction. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Nope, 14. That's all I needed to go. There's P prime. So now we can connect all of our dots. There's P prime, Q prime, Q prime, R prime, R prime, P prime. And if you kind of tilt your head to the right, a little cockeyed there, does it look like these two triangles are perfectly reflective of each other? And I'd say, yeah, we've got a pretty good case that that is absolutely true. So again, you could have used your rule on this, but again, I challenge you for future problems, try not to use your rule. Try to just do it the way I just showed you. But if you forget, you always have the rule. Now, to end with, reflecting across any other line besides a vertical or a horizontal line, like a y equals number or an x equals number, or the x-axis or the y-axis, or something perfectly diagonal is what I refer to, y equals x or y equals negative x. Like if you wanted to graph across the line, or reflect across the line, I should say, like x plus 2, you can't really do that just how we did it in this video. Because your reflected points aren't going to end up at what's called lattice points. And let me just show you real quick what a lattice point is. Like that's a lattice point. That's a lattice point. Where a point has no decimal value. This is exactly 3, this is exactly 4. So you're going to end up, with points like here. Like somewhere really random where you're like, oh, this is 4 point something, comma, negative 3 point something. That's why we're not going to do other crazy lines with graphing, okay? So don't worry about those. And that's it for video number 2. We'll see you video number 3.